Welcome back. Problem 12-35. This problem is taken from chapter number 12, that is Deflection of Beams and Shaft, and book name is Mechanics of Material by Rc Hibbeler. So statement is the beam is subjected to the load shown. Determine the equation of elastic curve. EI is constant. So you can see the beam and the loading over here. There is a moment at this end and at this end, and point A and B there is a pin support, and there is a uniformly distributed load of 3 kips per feet over a length of 8 feet. So you have to find the equation of elastic curve. So you need to find equation of elastic curve. So let's start with the solution. So first step is that if you remove this pin support at A, so you will be having a reaction force. Let this reaction force is Ra. And if you remove this pin support at point B, so you will be having a reaction force. Let this is Rb. So we have Ra and Rb, so we'll find them by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0 and taking the counterclockwise moment as positive. So about this point A, one moment is this 5 kips, that is a counterclockwise, so it will be positive. So I will write it 5. The second moment is due to this force Rb, and that is about point A, is perpendicular distance is 8 feet, and this is producing counterclockwise, so it will be also positive. So I will write minus plus Rb into 8. The third moment is this 5 kips into feet, that is clockwise, so minus 5. And the last moment that is produced due to this distributed load. So when this distributed load is converted into point load, so this will be equal to 3 into the length, which is 8 feet. So this is 24 kips force that is applied in the middle, and this perpendicular distance will be equal to 4 feet about point A. So this is 4 feet. So this is also producing clockwise movement, so it will be negative. So I will write minus 24 into 4, and that their sum must be equal to 0. So this 5 will cancel with this. So we have 8 Rb is equal to 24 multiplied by 4. So Rb is equal to 24 multiplied by 4 divided by 8. So we will get 12 kips. So Rb is equal to 12 kips. Now we will find Ra. So for Ra, we will use another equation of equilibrium, that sum of all forces along y direction must be equal to 0 when upward force is taken as positive. So Ra is upward and Rb is upward. So Rb is 12 kips plus Ra minus this 24 kips. Their sum must be equal to 0. So from here you will get Ra will be also equal to 12 kips. Okay, now we have Ra and Rb. So we will move to find the equation of elastic curve that can be obtained by using equation Ei into d square v over dx square is equal to moment. So we will find this moment by using Macaulay's method, Macaulay's function. So you can see here that you have moment, you have point loads, you have uniformly distributed load. So there is a table given in chapter number 12, that deflection of beam and shaft, and the table is 12-12. So here you can see for different type of loadings you have the equation of moment. So we will get the moment equation as the sum of all these functions. So first we will find the moment equation. So for that, if you draw this beam over here, let me draw it. So you can see at this end we have moment that is 5 kips into feet. Let this is your point A. So here there is a load of Ra that is acting Ra, and Ra is 12. Let this point is your point number B. So where you have Rb and uniformly distributed load between A and B. Let this is the uniformly distributed load. Okay, so this is acting downward. So now you can see that for movement we have this function, for concentrated load we have this function, and for uniformly distributed load we have this function. And this uniformly distributed load is 3 kips per feet. So what we will do is that if you look at case number 3, so uniformly distributed load starts from here till the end, but here you can see this distributed load starts from here till, but not till end. So what we will do is that we will bring it till the end, and we will subtract it in this portion, and this load will be upward in order to cancel the effect. So what we have done, we have added this in downward direction, and in order to cancel its effect, the same distributed load is also added but in opposite direction, so that these two cancel the effect. Now we will apply the equation of moment. So you can see from the table this moment will be equal to, first load is the moment, so we'll go to moment equation is this one. So here moment m naught is 5, so 5 into Macaulay bracket x minus a. Since you can see here this load, this is for the load of a, and this is the a distance. Since in this case the moment is at this point there, so a is equal to 0, so x minus 0 power 0. Now we'll move toward this point load. Also, you will have to be very careful that while you can see that the moment is in clockwise, here the moment is counterclockwise, so it will be negative. So for clockwise, the moment equation will be plus this one, and for counterclockwise, we will put negative. Now for P load, so you can see for point load, this P is upward, and that is acting at a distance of A from this end. Clear? So this is Ra. What will be the equation? This load is upward, P is upward, so plus, because the moment equation is this one. So we will replace P with Ra. So Ra is 12 into x minus A. Now here you can see A at a distance of 4 feet, so x minus 4 power 1. Okay, now another thing is that you have this distributed load. You can see that is starting from this point till end, and this is the case. But here the load is upward, so moment equation is this one. So I will write, since this is downward, so it will be negative. So minus W naught is 3, so 3 by 2 into x minus A. And again you can see A will be 4 because W starts from this point. So I will write x minus 4 power 2. Okay, the other thing is that we have this point load Rb, so Rb is upward, so plus Rb is again 12, and we will go to the point load moment equation, so P into x minus. Now distance of this point from this region is 12, so A is equal to 12 for Rb, so x minus 12 power 1. And we have the last thing is this uniformly distributed load which we have acted downward, so it will be plus W naught is 3, so 3 over 2 this is the equation 3 over 2 into x minus 12, because for this load, this distance, this is the A, and that is equal to 12. So this is your moment equation. Clear? And at the end we have moment of 5 kips, that will be skip. Okay. So once we have the moment equation will be like this: minus 5 into x minus 0 power 0 plus 12 into x minus 4 minus 3 divided by 2 into x minus 4 whole square plus 12 into x minus 12 power 1 minus 3 over 2 into x minus 12 whole square. So this is the main equation. If you have learned this, so next problem solution is very easy. So now you will put this equation, this A equation, and this is, let's say, number 1. So put equation A in equation number 1. So what we will get is that EI into d square V over dx square will be equal to moment, and moment will be equal to minus 5. X minus 0 is x power 0, so x power 0 is 1. So minus 5 plus 12 into x minus 4 minus 3 over 2 into x minus 4 whole square plus 12 into x minus 12 whole power 1 plus 3 over 2. This is plus 3 over 2 into x minus 12 square. Now integrate it once. Integrate it. So we will get EI into dV over dx will be equal to minus 5x plus 12 into x minus 4 whole square divided by 2 minus 3 over 2 into x minus 4 power cube divided by 3 plus 12 into x minus 12 power 2 divided by 2 plus 3 over 2 into x minus 12 power 3 divided by 3. So simplify it, we will get minus 5x plus 6 into x minus 4 whole square minus 1 over 2 into x minus 4 whole cube plus 6 into x minus 12 whole square plus 1 over 2 into x minus 12 whole cube. Okay, so while taking the integration of equation number this equation, so there will be a constant of integration as well, that will be C1. I will write C1. So EI into dV over dx. That this is your equation number 2. This equation will define you or give you the slope. Again, integrate equation number 2. So we will get EI, I will go direct, EI into V is equal to minus 5x square over 2 plus x minus 4 whole cube divided by 3. So 6 divided by 3 is 2 minus x minus 4 power 4 divided by 4, which is 1 over 8 plus x minus 12 whole cube divided by 3. So 6 divided by 3 is 2 plus x minus 12 whole power 4 divided by 4. So 1 over 2 multiplied by 4 is 1 over 8 plus C1x plus C2. And this is equal equation number 3. Now C1 and C2 are unknown constant of integration. And they will be defined by boundary condition. So we'll write boundary conditions. What are the boundary conditions? So first boundary condition is that at x is equal to 4 feet, we have deflection is equal to 0. So let me show you over here. So you can see at here x is equal to 4 feet. So we have deflection is equal to 0 because there is a support. Okay. So put in equation number 3, because equation number 3 is for deflection. So when you put in this equation, so we will get EI deflection is 0 is equal to minus 5 into x is 0. So this term will be equal to 0. So 0 plus this term will be equal to minus 4. So anything inside Macaulay bracket that is minus will be 0. Similarly, this term will be 0, this term will be 0, this term will be 0, and this term will be 0. So we will only left with C1, C2. And so from here you will get C2 is equal to 0. Okay. I think I made a mistake. We have to put x is equal to 4 feet. So make a correction that this will be not 0. So 5 minus 5 into x is 4, so 16 divided by 2. Plus this term is 0 because 4 minus 4 is 0. Minus 1 over 8, this term will be also 0. Because x minus 4 minus 4 is 0. Plus this term will be 4 minus 12, which is minus 8. So minus 8 Macaulay bracket, anything inside the Macaulay bracket is negative, will be negative, will be considered as 0. So 0, again this term will be also 0. Plus C1 into x, which is 4C1 plus C2. So we will get 0 EI into 0 is 0. So this will be minus 40 plus 4C1 plus C2. So we will get 4C1 plus C2 is equal to 40. This is your equation number 4. Now we will use another boundary condition, and this boundary condition is at x is equal to 12 feet, we have deflection is equal to 0. So we will put in equation 3. Let me show you here. Here you can see at x is equal to 12 feet, we have deflection is equal to 0 because there is a support. Clear? So we will put it in equation number 3. So equation number 3 is this one. So we will write EI into 0 is equal to minus 5 into 12 square divided by 2 plus 2 into 12 minus 4. 12 minus 4 whole cube minus 1 over 8 into 12 minus 4 whole power 4 plus 2 into 12 minus 12 will be 0 plus 1 over 8 into 12 minus 12 whole 4 plus C1x. X is 12. So 12C1 plus C2. So this will be equal to 0, and we will get minus 360 plus 1024 from this term minus 512 plus 0 plus 0 plus 12 C1 plus C2. So from here you will get 12c1 plus c2 will be equal to minus 152. This is your equation number 5. Now equation 4 and 5 are two simultaneous equation. So what we will do is that you can get from equation number 5, 12c1 is equal to minus 152 plus c2 minus c2, and c1 is equal to minus 152 over 12 minus c2 over 12. So this is the value of c1. So if you put this value of c1 in equation number 4, so you will get c1 is equal to minus 24. So once you get c1 is minus 24, so you can again put it in equation number 4, r5. So you will get c2 will be equal to 136. Now you have c1 and c2. So we have been asked to find the equation of elastic curve. So this is the equation, this equation number 3. So I will copy equation number 3 and we will move toward the next page. Let me copy it. Okay. So we'll remove these upper terms. So we get c1 is equal to, c1 was minus 24 and c2 was 136. So put c1 and c2 in equation number 3. So you will get ei into v is equal to minus 5x square over 2 plus 2 into x minus 4 power 3 minus 1 over 8 into x minus 4 power 4 plus 2 into x minus 12 whole power 3 plus 1 over 8 into x minus 12 power 4 plus c1 is minus 24 into x plus c2 is 136. And if you divide ei on both sides, so you will get deflection. Our equation of deflections come out to be 1 over e into I into minus 5 over 2 is 2.5 minus 2.5 x square plus 2 into x minus 4 power 3 minus 1 over 8 into x minus 4 power 4 plus 2 into x minus 12 whole cube plus 1 over 8 into x minus 12 power 4 minus 24 x plus 136. And this is the answer, our required equation of elastic curve that will give you deflection at any instant of time or any length. So if you want to find deflection at any length of x, so just put the value of x, so you will get the deflection at that point. And that was all about this problem 12-35. I hope you have enjoyed this video and you have learned from it. I have tried my best to describe it in a simple or smartest way, and I hope you have enjoyed this video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 12-36 that is taken from chapter number 12, Deflection of Beams and Shaft. And the book name is Mechanics of Material by Rc Hibbeler. So the statement of the problem is determine the equation of elastic curve, the slope at A and deflection of B of the simply supported beam. EI is constant. So you can see this is the simply supported beam where at point B there is a moment m0 and at point C there is also a moment that is m0. So due to this loading, the beam will bend like this. So we have to find the equation of elastic curve there, which is the equation of deflection. The slope at point A, this is the slope theta A, and deflection at point B. So this will be the deflection at point B, which is VB. So let's start with the solution. So first step is that if you remove this pin support, so there will be a reaction force. Let this reaction force is Ra, and if you remove this roller support at point D, so you'll be having a reaction force which is Rd. So we will find this Ra and Rd by using equation of equilibrium. So first equation of equilibrium is that sum of all movement about point A is equal to 0 and taking the counterclockwise movement as positive. So about point A, one movement is this m0, which is clockwise, so it will be negative. The other movement is this m0, which is counterclockwise, and that will be positive. And the third movement will be Rd into this length, which is L, and this will be again counterclockwise, so it will be positive. But the sum of all movement about point A will be equal to 0. So I will write minus m0 plus Rd into L is equal to 0. So from here you will get this Rd into L is equal to 0. So it means that reaction at point D is also equal to 0. So this is Rd. Now you'll find Ra by using another equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward forces taken as positive. So we have two forces, that is Ra, that is upward, plus Rd, which is equal to 0, is equal to 0. So from here you will get Ra is also equal to 0. Now you can see that this is 0 and this Ra is 0. So what we will do is that we are going to find out equation of elastic curve that can be found by using this formula Ei into d square V over dx square is equal to moment. So what we will do is that we will find moment by using singularity function, and you can see this table from here. You can see that we have the moments only. So what we will do is that if you go to the row number 1, that is about moment. If this moment is applied at a distance of A and x start from this place. There, so x start from this place, and you can see the moment equation will be first moment is this one, and this is at a distance of L by 3. So you can see this moment is clockwise, and this is also clockwise. So our equation will be equal to plus m0 into x minus A. So A will be replaced by L by 3. So x minus L by 3 power 0. The second moment is counterclockwise, so it will be minus m0 into x minus A. Remember, this is not parenthesis, this is Macaulay bracket. So, okay, m0 into x minus A. So x minus, now here for this m0, L will be equal to 2L by 3, because L by 3 plus L by 3 will give you 2L by 3. So A will be replaced with 2L by 3 and power will be equal to 0, because this is given in this formula. So this is your moment equation. If you simplify it, you will get the same this equation. So put this equation, let this is equation number A. So put the value of m in equation A, so you will get Ei into d square V over dx square will be equal to m0 into x minus L by 3 power 0 minus m0 into x minus 2L by 3 power 0. So what we'll do is that we will integrate this. So integrate it, you will get e into I d square v over dx square will be equal to m naught into x minus L by 3 power 1 divided by 1 minus m naught into x minus 2L by 3 power 1 divided by 1 plus C1. That this is your equation number 1. Now what we will do is that you have to again integrate equation 1. Again integrate equation 1. So you will get E into I into V, which is deflection, is equal to m naught into x minus L by 3 power 2 divided by 2 minus m naught into x minus 2L by 3 power 2 divided by 2 plus C1 into x plus C2. And this is equation number 2. Now C1 and C2 are unknown constant of integration and they can be found by using boundary condition. So boundary condition. So what are the boundary conditions? So first boundary condition is that at x is equal to L by 2, we have slope which is dv over dx will be equal to 0. So let me show, due to this loading, the beam will bend like this, clear? So you can see that here at x is equal, total length is L. So here at x is equal to L by 2. You can see if you take the tangent to this curve, so the slope will be equal to 0. So dv over dx will be equal to 0. So what we will do is that we have to put it in equation number 1. Put in equation 1. Now what is equation number 1? This is the equation of number 1. Okay, so here you have taken integration, so it will be dv over dx. Okay, so when you put dv over dx, this term is equal to 0, so you will get e into I into 0 is equal to m naught into L by 2 minus L by 3 power 1 minus m naught into x minus x will be replaced with L by 2, so L by 2 minus 2 L by 3 power 1 plus C1. Okay, so this is 0. This term will be equal to m naught into L by 2 minus L by 3 minus m naught into, this term will be 0 because you can see that L by 2 is less than from L by 2 L by 3, so this term will be negative, and anything inside the Macaulay bracket that is negative will be considered as 0. So I will write m naught into 0 plus C1. So from here you will get C1 will be equal to minus m naught into, if you take LCM, so it will be 6, so 3L minus 2L, and you will get C1 will be equal to minus m naught L over 6. So this is the value of C1. Now we will find C2 by using another boundary condition, and this boundary condition is that at x is equal to 0, we have deflection is equal to 0. So let me show you. Here you can see at x is equal to 0, deflection is equal to 0 because this is supported at point A. So we will put it in this equation number 2 because equation number 2 is about deflection. So here this term will become 0, and this term will be equal to m naught into 0 minus L by 3 power 2 minus m naught over 2 into 0 minus 2L by 3 power 2 plus C1x, which is m naught into L over 6 Sx plus C2. So this term will be equal to 0 because this will be negative. Anything inside the negative, inside the Macaulay's bracket that is negative will be considered as 0. Similarly, this term will be equal to 0. So we will left with 0 is equal to 0 minus m naught L, okay, over 6, and x is also 0. So this will be 0 plus C2. So from here you will get C2 will be also equal to 0. So you have C1 and C2 value. So what we have been asked to find the equation of elastic curve. So what we will do is that put C1 and C2 in equation number 2. So when you put it, you will get E into I into V is equal to m naught over by 2 into x minus L by 3 power 2 minus m naught by 2 into x minus 2 L by 3 square. C1 is minus m naught L by 6 into x, and C2 is 0. So divide EI on both sides. So what we will get is V is equal to 1 over EI into the same thing, which is m naught by 2 into x minus L by 3 whole square minus m naught by 2 into x minus 2 L by 3 whole square minus m naught L x by 6. Now what if you take m naught over 6 common? So m naught over 6 is common, and EI is also there. So you will get 3 into x minus L by 3 whole square minus 3 into x minus 2L over 3 whole square minus L into x. So if you multiply m naught over 6i, you will get the same equation that is mentioned above. And this is the required equation of elastic curve. Is required equation of elastic curve, or this is the equation of deflection. So if you put the value of x, so you will get the deflection at that point over the length of the beam. And this is the answer of our first part. Now we will move towards second part. And in second part, we have been asked to find the slope at point A. So what we will do is that put the value of C1 in equation number 1. Put C1 in equation number 1. So this is equation number 1. EI into dv over dx, EI into dv over dx into EI. So I will, okay, EI into dv over dx is equal to m naught into Lx, m naught into L minus x minus L by 3 power 1 minus m naught into x minus L 2L by 3 power 1 plus C1. So C1 is minus m naught L over 6. So divide EI on both sides. So we will get dv over dx is equal to 1 over EI into m naught minus x minus L by 3 m naught into minus m naught into x minus 2L by 3 minus m naught into L divided by 6. And if you take m naught over 6 as common, so this will be equal to m naught by 6. So you will have only this term x minus L by 3, x minus 2L by 3, and this will be equal to minus L only. Okay, so this is the equation of slope. I will copy it and we will move toward the second page. Copy it and I will paste it over here. So you will get this dv over dx is equal to slope. Okay, dv over dx is equal to slope, and that is equal to m naught over 6ei into x minus 6 minus xl by 3 minus 6 into x minus 2l by 3 minus l. Here is 6. So kindly make a correction here. When you take 6, so here you will be having 6, because when you multiply it, you will get the same equation. Okay. So this is the slope equation. Now we have to find the slope at point A. So here at x is equal to 0, we have slope will be equal to theta A. So at x is equal to 0, we have slope is equal to theta A dv over dx at x is equal to 0. So put the value of x in this equation B. Put in equation B. So what we will get is theta A will be equal to m naught over 6 ei into 6 minus x is 0 minus L by 3 minus 6 into 0 minus 2L by 3 minus L. So this value inside the Macaulay bracket will be negative, and anything inside Macaulay bracket that is negative will be considered as 0. So this will be 0 and this will be also 0. So we will be left with m naught over 6 ei into minus L. And this theta A will be equal to minus m naught L over 6 ei. So this is the value of slope at point A, and that is the answer of our second part. Now we'll move toward third part, and in third part we have been asked to find the deflection at point B. Let me show you the deflection at point B. That is x is equal to L by 3. So what we will do is that we will first copy the equation of deflection. This is the equation of deflection, or equation of elastic curve. Let me copy it, and we will move toward second page here. We will paste it. So this is equation of, so VB deflection at x is equal to L by 3. Okay. So at x is equal to L by 3. So put it in this, put x is equal to L by 3 in above equation of elastic curve. You will get deflection which is at point B will be equal to m naught over 6 ei into 3 minus 3 into L by 3 minus L by 3 power 2 minus 3 into L by 3 minus 2 L by 3 whole square minus L by 3 L minus L into L by 3. So it will be equal to m naught over 6 ei, that is deflection of beam, into this term will be 0. So 3 into 0 minus 3 into L by 3 is less than 2 L by 3. So this term, this whole term will be negative. So anything inside the negative, that is negative inside the column will be 0. So this will be 0. And we will left with L square over 3. And when you solve it further, you will get deflection at point B is equal to minus m naught L square over 18 ei. Or you can say deflection at point B is m naught L square 18 ei. And that is downward. Negative sign means the deflection is downward. So if you know the value of m naught, total length of the beam, modulus of elasticity, and I, so you can find the deflection at point B will be this one. Now we'll move toward problem 12-37, and that is the same question as 12-36, only the maximum deflection of simply supported beam is different. EI is constant. So in this question, we have to find equation of elastic curve and maximum deflection. So equation of elastic curve is already, we have find out in problem 12-36 there, so that we have explained earlier. And this was the equation of elastic curve. Now we find the maximum deflection. So you can see that maximum deflection due to the loading, the beam was bent like this. So maximum deflection will be this one at the mid of the beam. So at x is equal to L by 2, we have maximum deflection Vmax. So put x is equal to L by 2, where slope is dv over dx is equal to 0, and we have maximum deflection. So put it in this equation. So you will get Vmax is equal to m naught by 6 ei, and x will be 3 into x will be replaced by L by 2 minus L by 3 power square minus 3 into L by 2 minus 2L by 3 square minus L into L by 2. Okay, so this will become Vmax will become equal to m naught over 6 ei into 3 multiplied by this will, if you take the LCM, so this will be equal to 6. So 3L minus 2L square minus this term will be equal to 0 because L by 2 is less than 2L by 3. So it will be negative term. So this term will be equal to 0 minus 3 into 0 minus L square over 2. Okay. So we will get Vmax will be equal to m naught over 6 ei into 3 times L by 6 whole square minus L square over 2. So you will get m naught over 6 ei into 3L square over 36 minus L square by 2. So that will be equal to m naught over 6 ei. And if you take the LCM, that will be 72. So 72 divided by 36 is 2, and 2 into 3 is 6. So 6L square minus 72 is divided by 2 is 36. So 36L square. So you will get Vmax is equal to m naught over 6 ei into minus 30L square over 72. Okay. So 6 ones are 6, 6 5s are 30. So it will be minus 5 m naught L square over 72 ei. So Vmax is equal to minus 5 m naught L square over 72 ei. Or Vmax is equal to 5 m naught L square over 72 ei, and this will be, the deflection will be downward. And this is answer of our question number 12-37. And that was all about both this problem 12-36 and 37. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 12-38, that is from chapter number 12, deflection of beam and shaft by mechanics of material, Rc Hibbeler. And we'll solve this problem by using singularity functions or Macaulay's method. So statement is the beam is subjected to the loads as shown. Determine the equation of elastic curve EI is constant. So you can see this is the beam AB that is having pin support at point A and a roller support at point B. At this point, we have a load of 2 kips, and at this point, we have a load of 4 kips. And at the end, there is a movement clockwise that is 4 kips into feet. So we will find the equation of elastic curve. So let's start with the solution. So first step is that if you remove this pin support at point A, so you will be having a reaction force that is vertical, and this reaction force is AY, and there will be a horizontal reaction force which is represented as AX. And similarly, if you remove this roller support at point B, so you will be having reaction force which will be represented as RD. So we'll find this reaction forces by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see that one force is this upward, the second is this downward, third is this downward, and the fourth one is this upward. Their sum must be equal to 0. So I will write AY plus minus 2 minus 4 plus RB is equal to 0. So from here you will get AY plus RB will be equal to 6. That this is your equation number 1. Yeah. Now we will apply another equation of equilibrium, that sum of all movement above point A is equal to 0, and taking the counterclockwise movement as positive. So this is point A, so these two forces are passing through this point A, therefore they are not producing movement. So the first movement above point A is this 2 into perpendicular distance is 8, and this is producing clockwise, so it will be negative. The second movement will be due to this force into perpendicular distance is 16, and this is also clockwise, so it will be negative. And the third movement that is produced due to this load RB into perpendicular distance is 24, and it is producing counterclockwise, so it will be positive. And the last movement is this external movement which is clockwise, that is negative there. But the sum of all movement above point A will be 0. So I will write minus 2 into 8 minus 4 into 8 minus RB plus RB into 24 minus 4 is equal to 0. Okay, so this force 4 into this distance is 16, so this is 16, not 8. Their sum must be equal to 0. So I will write minus 16 minus 64 plus 24 RB minus 4 is equal to 0. So from here you will get 24 RB is equal to 84, and we will get RB is equal to 84 by 24, which is 3.5, and unit will be kip. Now you have this RB, and this is equation number 2. So put 2 in 1, put equation number 2 in equation number 1. So what we will get is that AY is equal to 6 minus 3.5, which is equal to 2.5 kip. So this is AY, and AX can be found by using equation of equilibrium. The sum of all forces along x direction must be equal to 0, and force taken in this direction is positive. So there is only AX, so AX is equal to 0. So we have AX as well. Now we will move toward equation of elastic curve. So we know that EI into d square v over dx square is equal to movement. So by using, we do not have movement, so by using Macaulay's method, we will find this movement M. And for that movement, you know that you will use the table, and you can now see that these are the point loads there. So we'll start from this left hand side, and at right hand side you have to neglect these two. So all are these point loads. So we will go to the table. This you can see here, this is the table for the point load. P is upward, so the moment equation is M minus P into X minus A, where X starts from this side, and this is acting at a distance of A. So if I copy this, so it will be helpful for us. So I will paste it over here. Okay. So now you can see for this movement, this is the load P, and for this load, first load AY. So P will be replaced with AY, and AY is 2.5. So 2.5 into, this is the moment equation, X minus A. So X minus A. So you can see here A is equal to 0. So X minus 0 power 1. The second load is this, and this load is downward, so this equation will be minus. So minus 2 into X minus, now A is 8, because this is X start from here. Clear? So X minus 8 power 1. The third load is minus 4 into X minus, now the total is 16, so X minus 16 power 1, and we will neglect the terms on the right side. So this is the moment equation. So I will write this moment equation, M will be equal to 2.5 times X minus 2 into X minus 8 minus 4 into X minus 16. Okay, so you can just put it in this formula. So you will get EI into d square V over dx square will be equal to this 2.5 X minus 2.2 into X minus 8 minus 4 into X minus 16. So what we will do is that we will integrate it once. So when you integrate it, you will get EI into dv over dx will be equal to 2.5 X square divided by 2 minus 2 into X minus 8 power 2 divided by 2 minus 4 into X minus 16 power 2 divided by 2 plus C1. So this equation will become EI into dv over dx become equal to 1.25 X square minus X minus 8 power 2 minus 2 into X minus 16 power 2 plus C1. That this is your equation number 1. Again integrate equation number 1. So you will get EI into V, which is deflection, is equal to 1.25 whole cube divided by 2 minus X minus 8 power 3 divided by 3 minus 2 into X minus 16 power 3 divided by 3 plus C1 X plus C2. So if you simplify it further, so you will get EI into V is equal to 0.417 x cube minus 0.333 into x minus 8 power 3 minus 0.667 into x minus 16 power cube plus C1x plus C2. Let this is your equation number 2. Now we know that C1 and C2 are unknown constant of integration, and they can be found by using boundary condition. So what are these boundary conditions? So the first boundary condition is that at x is equal to 0, we have deflection V is equal to 0. So you can see here x is equal to 0, deflection will be equal to 0 because this is a pin support. Clear? So put it in equation number 2 because equation number 2 is about deflection. So when you put this V is equal to 0, so this term will be equal to 0, this term will be equal to 0, this term will be 0 because it will be minus 8 Macaulay bracket. So anything inside Macaulay bracket which is negative will be considered as 0. This will be also 0, this will be 0. It means that C2 will be equal to 0. So I will write C2 is equal to 0. Now we'll use second boundary condition. And what is this second boundary condition? So second boundary condition is that at x is equal to 24 feet, we have deflection is equal to 0. And we will also put in equation number 2. But let me show here x is equal to 24 feet. So we have deflection is equal to 0 because there is a support at this point. Okay. So you will put it in this formula. So I will write EI into 0 is equal to 0.417 into 24 power 3 minus 0.333 into 24 minus 8 power 3 minus 0.667 into 24 minus 16 power cube plus C1 into x, and x is 24, so 24 C1 and C2 is equal to 0. So it will be equal to 0, and this term will be equal to 5760. The second term will give you minus 1365.33 minus the third term will give you 341.33 plus 24 C1. 24 C1. So when you calculate it, you will get C1 will be equal to minus 169. So now you have C1 and C2. So what you will do is that put C1 and C2 in equation number 2 to get the equation of elastic curve. So you will get EI into V is equal to 0.417 x cube minus 0.333 into x minus 8 power cube minus 0.667 into x minus 16 power cube plus C1. C1 is minus 169 into x, and C2 is equal to 0. So again, if you divide EI on both sides, so you will get V is equal to 1 over EI into 0.417 x cube minus 0.333 into x minus 8 power cube minus 0.667 into x minus 16 power cube and minus 169 x, which is the required equation of elastic curve. And this is the answer. So if you want to find the deflection at any point of x, so put the value of x, that x in this equation, and E and I. So you will get the deflection value at that x along length, along the beam length or shaft length. And that was all about this problem 12-38. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, and I will request them to subscribe it and press the bell icon so that they may get notification about my every latest video which I post. If you have any question, you can ask me in comment section. Also, I have pasted all the links of playlists of every chapter. So if anyone interested, so he or she can click on the link and he will get all the problems of that chapter. Thank you for watching. Welcome back. Problem 12-39. So this problem is taken from chapter number 12, that is deflection of beam and shaft, and book name is Mechanics of Material by Rc Hibbeler. So statement is determine the maximum deflection of the cantilever beam. The beam is made of material having E is 200 GPa and I is 65 into 10⁻⁶ millimeter power 4. So you can see this is a cantilever beam that is fixed at point A, and at this end we have 15 kN load, and from point A till length of 1.5 meter there is a uniformly increasing load, a triangular load that is 30 kN per meter. So due to this load, the beam will deflect like this. So we have to find the maximum deflection of the cantilever beam, that will be at this end, Vmax. Okay. So let's start with the solution. So first step is that if we remove this support, fixed support at point A, so you will be having a reaction force, that this force is Ra, and there will be a moment which is represented as Ma. And you can see that this is a triangular load, so if you want to convert it into point load, so this will be 1 over 2 into 30 multiplied by the length over which it acts, that is 1.5. Clear? And this will act at a distance of L by 3. So L is here 1.5, so 1.5 divided by 3 will give you 0.5 meter, and this remaining distance will be 1 meter. Now we will apply equation of equilibrium for finding this Ra and Ma. So first equation of equilibrium is that sum of all forces in y direction must be equal to 0, and upward force is taken as positive. So one force is Ra, the second one is this one, and third one is this one. Their sum must be equal to 0. So Ra is upward, so we write Ra plus. The other one is downward, so 1 over 2 into 30 into 1.5. And the third one is minus 15 is also downward, so their sum must be equal to 0. So from here we will have Ra minus 22.5 minus 15 will be equal to 0, and this Ra will be equal to 37.5 kilonewton. Okay. So this is the value of Ra. You will find moment. So for moment we will apply equation sum of all moment about point A is equal to 0, taking the counterclockwise moment as positive. So about this point A, this Ra is passing through this point, so it is not producing moment. So first moment is this one, which is the reaction moment, that is Ma, and that is counterclockwise, so it will be positive. So Ma, the second moment will be produced due to this force into perpendicular distance is 1 meter, and this is producing clockwise, so it will be negative. So I will write minus 1 over 2 into 30 into 1.5 multiplied by perpendicular distance is 1. The other moment that is produced due to this 15 into perpendicular distance is this one, which is 3 meter, and this is also producing clockwise, so it will be negative. So I will write minus 15 into 3 is equal to 0. So Ma minus 22.5 minus 45 is equal to 0. So from here you will get moment, reaction moment at point A comes out to be 67.5 kilonewton into meter. So you are having this reaction moment. Now what we are going to find, we are going to find out the maximum deflection, for which we need the equation of elastic curve. So equation of elastic curve can be found by using this formula: EI into d square V over dx square is equal to moment. So we'll find the moment equation for this beam, and you can see that we have this table, and in row number 4 you can see the loading slope. In 1 you can see the moment, in 2 you can see the loading, that is point load, and in 3 you have distributed load. So what if I draw the free body diagram? Okay, so if I draw the free body diagram of this beam, so it will be like this, where you have Ra, that is equal to 37.5 kilonewton. You have moment, which is 67.5 kilonewton into meter. Okay, now you can see that here you have a load, uniformly increasing load, and this is up till this length. And from this table you can see this uniformly distributed load starts from here till the end here, and this is at a distance from of A from this. Let's start from this. So what we will do is that we will convert. We have this load, uniformly increasing load till the mid. Okay, like this is the mid. So we have uniformly increasing load like this, which is 30 kilonewton per meter. So what we will do is that we will add, this is at a distance of 1.5 meter from this side. So 1.5 meter, and the remaining is also 1.5. Okay, so just remember this is 1.5. So if we move it till the end, because in table it is till the end, so this will be the load. Now you can see this load will be like this one. And the amplitude of load at this point, we have a load of 30 kilonewton per meter. But here at this point, the load will be 16 kilonewton per meter, because this is of length of 1.5 meter. So same is the case if you look at this. So we can divide it like this. So this is 30 kilonewton per meter. So same, in order to cancel the effect, so we will add the same 30 kilonewton that will be acting upward. And now this remaining portion, that will be also upward. So this is 30 kilonewton per meter, and this will be also, at this point we will also have 30 kilonewton per meter, and the sum of this plus this will be 60, which will cancel the effect. Now at this end we also have a point load of 15 kilonewton. So I will choose another color. At this end we have 15 kilonewton. Now we will use this table in order to find the equation of moment. So I will write it. You can see first we will take this Ra, R37.5, that is point load. So you will consider this equation, moment equation. So M is P into X minus A. So P will be 37.5 into X minus. Now here A is equal to 0, because it will start from it will act from this starting point. So X minus 0 power 1. Now we'll take this moment, which is this one, and that is the moment equation will be this one. Okay. So since this moment is clockwise, so this is positive. So here the moment is counterclockwise, so it will be negative. So minus 67.5 into X minus A is also again 0, because the moment is acting over here. Here. So A will be equal to 0. So X minus 0 power 0. Now we will take this uniformly increasing load till this point, and this is triangular load. So for triangular load, we will choose this formula. What is small m? So small m is slope, and slope of this triangular load will be equal to perpendicular, this perpendicular over this base. So perpendicular is 60, and base is total length is 3. So I will write m is equal to 60 divided by 3, which is equal to 20. So m is equal to 20. So I will write this moment equation, and this load is downward and this is upward. So this will be minus m by 6. So m is 20. So 20 divided by 6 into x minus 0. Why 0? Because this load starts from this, x is equal to 0. So A is equal to 0 over here. Okay. Now we have this load, which is 30, and this load you can see is uniformly distributed load, or length of 1.5 meter. So this is the equation of uniformly distributed load, and the load is upward, so it will be plus W0, which is 30 divided by 2 into x minus. Now this load starts from here. So this A is equal to 1.5. So x minus 1.5 power 2. And we will left with the last one, which is this one. This uniformly increasing load. And for uniformly increasing load, we again will move toward this equation. So that is load is upward, so it will be plus m. So m here, m2 will be equal to this perpendicular, which is 30, and base is 1.5, which is also give you 20. So it will be equal to 20 divided by 6 into x minus 1.5, because it is here A is equal to 1.5 power 3. Okay, so there is 3 over here. Now if you further simplify it, so you will get moment will be equal to 37.5 into x minus 67.5. X power 0 is 1, so minus 20 divided by 6 will be 10 by 3. So 10 divided by 3 into x cube, and this term will be also 10 by plus 10 by 3 into x minus 1.5 times cube, and this term will be plus 15 into x minus 1.5 times square. So this is your moment equation. So put it in this formula. So you will get EI into d square V over dx square will be equal to 37.5x minus 67.5 minus 10 over 3x cube plus 10 by 3 into x minus 1.5 cube plus 15 into x minus 1.5 whole square. So what we will do is we will integrate this equation, integrate it. So you will get EI into dV over dx will be equal to 37.5 x square divided by 2 minus 67.5 x minus 10 into x power 4 divided by 4 into 3, which is 12, plus 10 by 10 into x minus 1.5 power 4 divided by 4 into 3, 12, plus 15 into x minus 1.5 whole cube divided by 3 plus C1 x. And if you further simplify, it will be equal to 18.75 x square minus 67.5 x minus 5 by 6 x power 4 plus 5 by 6 x minus 1.5 power 4 plus 5 into x minus 1.5 power cube plus C1. Sorry, it is C1, not C1x. So that this is your equation number 1. So what we will do is that since we are interested to find out the equation of elastic curve, so integrate equation number 1, integrate equation 1. So when you integrate it, you will get EI into V, which is deflection, is equal to 18.75 x cube divided by 3 plus minus 67.5 x square divided by 2 minus 5 into x power 5 divided by 6 into 5, which is 30, plus 5 into x minus 1.5 power 5 divided by 6 into 5 is 30, plus 5 into x minus 1.5 power 4 divided by 4 plus C1 x plus C2. And if you further simplify it, you will get 66.25 x cube minus 33.75 x square minus 1 over 6 x power 5 plus 1 over 6 into x minus 1.5 power 5 plus 5 by 4 into x minus 1.5 power 4 plus C1 x plus C2. So this is your equation number 2, and that is equal to EI into V. Now C1 and C2 are unknown constant of integration, so we can find by using boundary conditions for finding C1 and C2. So first boundary condition is that at x is equal to 0, we have slope dV over dx will be equal to 0. So let me show you over here. I have already told you in the start that due to this, the beam will deflect like this. Clear? So here at x is equal to 0, we have slope which is dV over dx is equal to 0, because this will be a straight line. So tangent to this straight line will give you slope. So what we will do is we will put in equation 1. So when you put it in equation 1, so dV over dx is equal to 0, this term will be equal to 0, x is 0, this term will be 0, this term will be 0, this term will be 0, and 0 minus 1.5 is minus 1.5 power 4. So anything inside Macaulay bracket which is negative will be considered as 0. So this will be 0 and this will be also 0. It means that C1 is equal to 0. So I will write, you will get C1 is equal to 0. Now the second boundary condition is that at x is equal to 0, we have deflection V is equal to 0. So here you can see this end is fixed support. So at x is equal to 0, we have deflection is equal to 0. So we will put in equation 2. So this is the equation number 2. So this term will be 0, x is 0, so this term will be 0, this term will be 0, this term will be 0, and 0 minus 1.5 is minus 1.5 power 5, and this is inside the Macaulay bracket, so any negative term inside the Macaulay bracket will be 0. So this will be 0, and C1 into x is 0, so it means C2 is also 0. So from here you will get, you can just put it, I am skipping it so that to save the space. So C1 and C2 is equal to 0. So what we will do is that put C1 and C2 in equation number 2, that is about deflection. So we get EI into V is equal to 6.25 x cube minus 33.75 x square minus 1 over 6 x power 5 plus 1 over 6 into x minus 1.5 power 5 plus 5 over 4 into x minus 1.5 power 4. C1 and C2 are 0, so this will be the equation. And if you divide EI on both sides, so you will get V is equal to 1 over EI into 6.25 x cube minus 33.75 x square minus 1 over 6 x power 5 plus 1 over 6 into x minus 1.5 power 5 plus 5 over 4 into x minus 1.5 power 4. And this is the required equation of elastic curve. Now in question we have been asked to find the maximum deflection. So maximum deflection will occur at the free end. This is the maximum deflection. This is maximum deflection. And this occur at x is equal to 3 meter. So put x is equal to 3 meter in this equation. So you will get Vmax will be equal to 1 over EI into 6.25 3 cube minus 33.7 into 3 square minus 1 over 6 3 power 5 plus 1 over 6 into 3 minus 1.5 power 5 plus 5 over 4 into x, which is 3 minus 1.5 power 4. So again, when you solve this, you will get Vmax will be equal to minus 167.91 over EI. Okay. So now you have the value of E and I as well. That is given 200 gigapascal and I 65 into 10 to the power 6. So put it minus 167.91. This will be, the unit will be in kilonewton, so I will multiply 10 to the power 3 because this all the loads were in kilonewton. Okay. So divide by E, which is 200 gigapascal, 200 into 10 to the power 9, and I is 65 into 10 to the power minus 6. This is minus 6. Okay. This is plus 6. So that is I is 65 into 10 to the power 6, and when you convert it into meter, so meter power 4, so there will be 10 to the power minus 12 meter power 4. So this will be 65 into 10 to the power minus 6 meter power 4. So I will write 65 into 10 to the power minus 6, and when you calculate it, you will get Vmax will be equal to minus 0.01292 meter, or you can say Vmax is equal to minus 12.9 millimeter, or Vmax is equal to 12.9 millimeter, and that is downward. So this is the maximum deflection of the beam for the given loading. And that was all about this problem 12-39. I hope you have enjoyed this video. I will prefer you to now practice it by your own so that you have a clear understanding. Again, those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 12-40. So this problem is taken from chapter number 12, Deflection of Beam and Shafts, and the book name is Mechanics of Material by Rc Hibbeler. So statement is determine the slope at A and deflection of and C of overhang beam E is equal to 29 to 10 power 3 KSI and I is 204 inch power 4. So you can see this is an overhang beam and there is a pin support at point A and a roller support at point B. And at this point we have a 6 kip load, and from B to C there is a uniformly distributed load of 2 kips per feet, and at point C we have 3 kip point load. So due to this loading, the beam will deflect like this. Clear? So we have to find the slope at this point, which is theta A, and deflection at point C. So let's start with the solution. So first step is that if you remove this pin support, so you'll be having a reaction force. Let this reaction force is Ra, and if you remove this roller support, so you'll be having a reaction force which is represented as Rb. So we will find this Ra and Rb by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0 and taking the counterclockwise moment as positive. So first moment about point A will be due to this load, which is 6 into perpendicular distance is 6, and this is producing clockwise, so it will be negative. So I will write it first, 6 multiplied by 6, and that will be negative 1. The second moment that is produced due to this Rb force, and this Rb into perpendicular distance is 12, and that is producing clockwise, counterclockwise, so it will be positive. So I will write plus Rb into 12. The third moment that is produced due to this distributed load when converted into point load, so this will be equal to 2 into our length, that is 6, is equal to 12 kip. And that will act at a distance of 3, because 6 divided by 2 is 3. That will act in the middle. So this is 3 and this is also 3 feet. So due to this load, point loads, there will be a moment, and the perpendicular distance is now 15, and this is producing clockwise, so it will be negative. So I will write minus 12 into 15, and the last moment is due to this load, which is 3 kips into perpendicular distance is 18, and this is also producing clockwise, so it will be negative. So I will write minus 3 into 18 is equal to 0. So minus 36 plus 12 Rb minus 180 minus 54 is equal to 0. So from here you will get 12 Rb will be equal to 270, and Rb will be equal to 270 divided by 12, which will give you 22.5 kips load. So this is the value of Rb. Now we will find Ra by using equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So Ra is upward, so I will write Ra, this is minus because it is downward, so minus 6 plus Rb, which is upward, and that is 22.5, minus this 12 kips load, and minus 3 will be equal to 0. So from here you will get Ra will be equal to 1.5 kip. Now you have both Ra and Rb, so we will go toward equation of elastic curve that can be obtained by using this formula, Ei into d square V over dx square is equal to moment. So we will define the moment for this overhang beam. So for that you can see all the loads. This load is point load, this is also point load, this is point load, and this is distributed load, and we will neglect this load. Yeah. So for that we will need table. So I'm going to copy it from my previous problem, and we will paste it over here. Okay, so we will take the help from this table. So moment equation will be equal to, moment equation will be M will be equal to, first load is point load Ra. So we will go toward this, and this is the moment equation. So load is upward, so it will be positive. So P will be replaced with Ra, and Ra is 1.5. Okay, so this is 1.5. Okay, so kindly make a correction. This Ra is negative, so it means that our assumed direction, which was upward, was wrong. So R should be in downward direction. Yeah. Now you can see we'll start from this load Ra. So moment equation will be this one. So load is upward, so this is positive. Their load is downward, so it will be minus 1.5 into x minus a. So a is equal to 0 over here. So x minus 0 power 1. The second load is this 6 kips. So again the same function will be used, and load is downward, so it will be minus. So 6 into x minus, now a is equal to 6 because x start from here. So a will be equal to 6. So x minus 6 power 1. The third load is Rb, that is upward, so it will be plus, and Rb is 22.5 into perpendicular into distance x minus total distance is this one, which is 12 feet. So A is equal to 12 feet. Here power 1. And the last thing is that you have a uniformly distributed load that starts from here till the end, and the distance A is for this load is 12. So we will go toward this equation. You can see this is for uniformly distributed load. So this load is downward and this is upward. So this function will be, in our case, it will be minus. So minus M minus W naught. W naught is 2 kips. So 2 divided by 2 into x minus 12 power 2. So this is the equation of, I will write it again, moment is equal to minus 1.5 x minus 6 into x minus 6 plus 22.5 into x minus 12 power 1 minus x minus 12 square. So this is the moment equation. Now you will put that this is your equation number A. So put the value of M in equation A. So you will get Ei into d square V over dx square is equal to minus 1.5x minus 6 into x minus 6 plus 22.5 into x minus 12 minus x minus 12 power 2. So what we will do is that integrate this equation, integrate it. So you will get Ei into dv over dx will be equal to minus 1.5 x square divided by 2 minus 6 into x minus 6 power 2 divided by 2 plus 22.5 into x minus 12 power 2 divided by 2 and minus x minus 12 power 3 divided by 3. And plus there is a constant of integration which is c1. So if you further simplify it, it will be equal to ei into dv over dx is equal to minus 0.75 x square minus 3 into x minus 6 square plus 11.25 into x minus 12 square and minus 0.33 or 1 over 3 into x minus 12 whole cube plus c1. That this is your equation number 1. Now what we will do is that integrate equation number 1. So you will get e into I into v is equal to minus 0.75 x cube divided by 3 minus 3 into x minus 6 power 3 divided by 3 plus 11.25 into x minus 12 power 3 divided by 3 minus 1 over 3 into x minus 12 power 4, and we will multiply with this 3 plus c1 into x plus c2. So you will get ei into v is equal to minus 0.25 x cube minus 3 into 3 and 3 will cancel, so only we left with x minus 6 power 3 plus 3.75 into x minus 12 cube minus 1 over 12 into x minus 12 power 4 plus c1x plus c2. And this is your equation number 2. So for finding c1 and c2, these are unknown constant of integration. So by using by boundary conditions, we will find c1 and c2. So what are the boundary conditions? So at first boundary condition is that at x is equal to 0, we have deflection is equal to 0. So let me show you here x is equal to 0. So you can see this is a pin support, so deflection will be equal to 0. So what we will do is that put in equation number 2. Why? Because equation number 2 is about deflection. So when you put it in this equation, this is the equation. So ei into 0 is equal to minus 0.25 times 0 cube minus 0 minus 6 whole cube plus 3.75 into 0 minus 12 whole cube minus 1 over 12 into 0 minus 12 whole power 4 plus c1 into 0 plus c2. So you can see this will give you 0 and this will be minus 6. Anything inside Macaulay bracket will be considered as that will be negative will be considered as 0. So minus 0 plus this term will be also 0 because minus 12 in the Macaulay bracket will be 0. This will be also 0. c1 into 0 is 0 plus c2, and this is equal to 0. So from here you will get c2 is equal to 0. Now we have c2 is equal to 0. We'll use second boundary condition, and second boundary condition is that at x is equal to 12 feet, we have deflection is equal to 0. So let me show you over here. So you can see at point B, x is equal to 12 feet. This is the total distance. So here deflection is equal to 0 because there is a roller support. So put this in equation number 2. So I will put it. We will get ei into 0 is equal to minus 0.25 into 12 cube minus 12 minus 6 cube plus 3.75 into 12 minus 12 whole cube minus 1 over 12 into 12 minus 12 whole power 4 plus 12 c1 and c2 was 0. So 0, and this will give you minus 0.25 into 12 cube minus 6 cube plus this will be 0, 12 minus 12 is 0, and the same this term will be 0 plus 12 c1. So when you calculate it, it's very easy. Take the 12 cube and multiply it with minus 0.25 and then minus 6 cube and then solve this. So you will get c1 will be equal to 54, and the unit will be, if you do not write it's okay, but unit will be gives into feet square feet. So this is c1. Now we have c1 and c2. So what we will do is that put c1 and c2 in equation number 1. Why? Because in our first part we have been asked to determine the slope at A. So equation 1 is about slope. This is equation number 1. You can check if this is the equation number 1. So when you put it, so you will get ei into dv over dx is equal to minus 0.75 x square minus 3 into x minus 6 power square plus 11.25 into x minus 12 power 2 minus 1 over 3 into x minus 12 power 3 plus c1, which is 54. So if you divide ei on both sides, so you will get dv over dx, which is again equal to slope, and that is equal to 1 over ei multiplied by minus 0.75 x square minus 3 into x minus 6 square plus 11.25 into x minus 12 square minus 1 over 3 into x minus 12 whole power 3 plus 54. So this is the equation of slope. Now we have to find the slope at point A. So at point A is this one. So it means that at x is equal to 0, we have to find the slope at A. So put x is equal to 0. So this dv over dx at x is equal to 0 will be equal to slope at point A and 1 over ei into minus 0.75 0 square minus 3 into 0 minus 6 whole square plus 11.25 into 0 minus 12 whole square minus 1 over 3 into x minus 12 whole cube plus 54. So we will get theta A is equal to 1 over ei, and this term will be 0, this will be 0, plus 0, minus 0, plus 54. So we will left with theta A is equal to 54 over ei, and the unit will be gives into feet square. Now we have E and I as well. E is 29 into 10 to the power 3 ksi kilopound per square inch, and I is also 204 inch power 4. So what we will do is that we will convert this theta A is equal to 5 kips. So 10 to the power 3, you have to multiply 10 to the power 3, or if you do not want to convert it into pounds, so 54, and we will convert feet into inch. So 1 feet is 12 inch. So 12 power 2 divided by E, which was 29 ksi. So 29 into 10 to the power 3, 29 into 10 to the power 3 ksi. So ksi is there into 204. So when you solve this, you will get theta A comes out to be 0.0131 radian. So this is theta A, which is 0.00131 radian. If you want to convert it into degrees, so multiply. We know that 2 pi radian is equal to 360 degree. So 1 radian is equal to 180 divided by pi. So multiply it, so you will get the theta A in degrees. So this is answer of our first part. Now we will move towards second part, and in second part we have been asked to find the deflection at point C. So what we will do is that we will copy the equation number 2. Let me copy it. This is equation number 2, and note down the value of C1 and C2. So C1 was 54 and C2 is 0. Move toward next page. So this is equation number 2. Okay. So put C1 is equal to 54 and C2 is equal to 0 in equation 2 to get the equation of elastic curve. So UV is equal to, and divide EI on both sides. So 1 over EI into minus 0.25 x cube minus x minus 6 cube plus 3.75 into x minus 12 cube minus 1 over 12 into x minus 12 power 4. C1 is 554, so 54x, and C2 is equal to 0. Now we have been asked to find the deflection of NC. So at here you have to find deflection. So x will be equal to 18 feet. So you have to find deflection, which is BC. So put x is equal to 18 feet. We will get deflection at x is equal to 18 feet is equal to deflection of point C, and that will be equal to 1 over E into I, and x minus 0.25 times 18 cube minus 18 minus 6 cube plus 3.75 into 18 minus 12 cube minus 1 over 12 into 18 minus 12 power 4 plus 54 multiplied by 18. Okay. So again, when you solve this, you will get deflection at point C comes out to be 1512 kips into feet cube. Unit will be this, and divide by E into I. So we have E and I. So 1512, E is 29 into 10 to the power 3 ksi, and I is 204. But here we have feet, so we convert 1 feet is 12 inch, so 12 cube. And when you solve this value will be negative 1. So when you solve this, you will get deflection of point C will be equal to minus 0.442 inch. Or you can see that deflection of point C is 0.442 inch, and that will be downward. So this is the answer of our second part. And that was all about this problem 12.40. I hope you have enjoyed this video and you are learning from my videos as well. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest video which I post. And if you have any question, you can ask me in comment section. Thank you for watching. Also share my channel with your friends and help me in growing my channel. Welcome back. Problem 12-41. This problem is taken from chapter number 12, that is deflection of beam and shaft, and the book name is Mechanics of Material by Rc Hibbeler. So statement is determine the maximum deflection in region AB of overhang beam. E is 29 into 10 to the power 3 ksi, and I is 204 inch power 4. So you can see this is overhang beam that is acted upon by load of 6 kips at a distance of 6 feet from point A, and there is just uniformly distributed load from B to C, and this load is 2 kips per feet. And at point C we have a 3 kips load. So due to this loading, this beam will deflect, or this beam will bend like this. So you have to find the maximum deflection in region AB. So let's start with the solution. So first step is that if you remove this force, if you remove this roller support, so you'll be having a reaction force. Let this force is known as RB. And if you remove this pin support at point A, so you'll be having a reaction force in that will be downwards. So that will be RA. So you can take it as per your own choice, but when you calculate it from the result value, you will then know that whether I have choose the corrected direction or not. So you'll find RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all movements about point A is equal to 0 and taking the counterclockwise movement as positive. So this is point A and this RA is passing through it, so it is not producing movement. So first movement that is produced by this force, which is 6 into perpendicular distance, is 6, and this is producing clockwise movement, so it will be negative. So I will write minus 6 times 6. The second movement that is produced due to this force RB, and this RB into perpendicular distance is 12, and this is producing counterclockwise, so it will be positive. So I will write plus RB into 12. Now third movement that is produced by this uniformly distributed load when it is converted into point load. So how you will convert it? So this is the magnitude of the load, distributed load into its length will be converted into point load. That will be 12 kips, and that will act at a distance at a half of this 6 feet. So it will be 3 feet. This will be 3 feet. So this force will produce movement, and this force at perpendicular distance is now this 12 plus 3 is 15, and this is producing clockwise, so it will be negative. So I will write minus 12 into 15. The last moment that is produced by this 3 kips force into perpendicular distance is now 18, and this is producing clockwise, so it will be also negative. So I will write minus 3 into 18 is equal to 0. So minus 36 plus 12 RB minus 180 minus 54 is equal to 0. So 12 RB is equal to 270, and from here you will get this RB will be equal to 270 divided by 12, which is 22.5 kip. So this is your RB. Now we will find RA by using another equation of equilibrium, that is sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So from here you can see one force which is RA, that is downward, so minus RA minus 6 kips, which is this one, plus RB, which is 22.5, minus 12 kips, minus 3 is equal to 0. So we will get RA will be equal to minus 6 minus 12 is minus 18, minus 3 is minus 21. So plus 22.5 minus 21 will be 1.5 kips. Since this value is positive, it means that our assumed direction of taking A downward is right. Now you have RA and RB. So what we will do is that we know that equation of elastic curve can be obtained by using this formula EI into d square V over dx square is equal to moment. So we'll find this moment by using discontinuity function or Macaulay's method. So what does Macaulay's method tell us? So if you look at this, this is a point load. Clear? There is a point load. There is a point load. There is a distributed load from here, and we will neglect the last force. This 3 kips. So we'll start from left hand side and move toward right hand side, and we will neglect the last one. So for that we have a table. So let me copy it. This is the table that is available in book chapter, that is chapter number 12. So from this table you will take the moment equation as per your required loading. So first starting from this RA, so you can see this is a point load that is acting, and X start from here. Okay, so first load is P. Now you can see this is the case number 2. So here point load is acting, but this point is acting, this load is acting at a distance of A from this X. Clear? So moment function is this one, and this load is upward, so this is positive. Here this load is downward, so we will take moment as negative. So moment will be equal to minus RA is 1.5 into X minus A. So A here is equal to 0, so X minus 0 power 1. The second load is this 6 kips load, and this is downward, so same minus 6 into X minus, now A is equal to 6. So X minus 6 power 1. The third load is RB, so it will be upward. It is upward, so it will be positive. Moment will be P into P will be replaced by RB, which is 22.5 into X minus A. So here A is now 6 plus 6, which is 12 feet. X minus 12. And there is a uniformly distributed loads. You can see over here. Now we will choose this case. So this load is acting upward, so moment equation is this one. Here this load is downward, so we will take the it negative. So minus this function tells us W0 over 2. So W0 is 2, so 2 over 2 into X minus A is for this load is again, this is 12 because this is starting from this point. So A, this distance is A. Okay, so this distance is A, so A minus X minus 12 power 2 because this is available, this is square. So this is the moment equation. If I further simplify it, so this moment will be equal to 1 minus 1.5 X minus 6 into X minus 6 power 1 plus 22.5 into X minus 12 minus X minus 12 power 2. Now this is your equation number A. So what we will do is that put value of M in equation A. So you will get EI into d square V over dx square will be equal to minus 1.5 X minus 6 into X minus 6 power 1 plus 22.5 into X minus 12 into minus X minus 12 power 2. Now integrate it once, integrate it. So you will get EI into dV over dx is equal to minus 1.5 X square over 2 minus 6 into X minus 6 power 2 divided by 2 plus 22.5 into X minus 12 power 2 divided by 2 and minus X minus 12 power 3 divided by 3. Plus there will be a constant of integration which is C1. So if you further simplify it, you will get EI into dV over dx will be equal to minus 0.75 X square minus 3 times X minus 6 square plus 11.25 into X minus 12 square minus 1 over 3 into X minus 12 whole square whole cube plus C1. Let this is your equation number 1. Okay. Again integrate this equation number 1. So what we will do is we will integrate it. So you will get EI into V is equal to minus 0.75 X cube divided by 3 minus 3 into X minus 6 whole cube divided by 3 plus 11.25 into X minus 12 power 3 divided by 3 minus 1 over 3 into X minus 12 power 4 divided by 3. So it will be multiplied with 3 and that will be equal to 12. Okay, minus plus C1x and there will be another constant of integration which is equal to C2. So if you further simplify it, you will get EI into V is equal to minus 0.25 X cube minus X minus 6 power 3 plus 3.75 into X minus 12 power 3 minus 1 over 12 into X minus 12 power 4 plus C1x plus C2. That is, this is your equation number 2. So C1 and C2 can be obtained by using boundary conditions. So boundary conditions are used to find C1 and C2. So first boundary condition is that at X is equal to 0, we have deflection is equal to 0. So let me show you over here. Here X is equal to 0, so we have deflection is equal to 0 because there is a pin support. So put in equation number 2. Put it in equation 2. So you will get this term will be 0. This term will be, this X is 0, so this will be 0. And this 0 minus 6 will be minus 6. That will be inside Macaulay bracket. So anything that is negative inside Macaulay bracket will be 0. Similarly, this will be 0 because minus 12 inside the Macaulay bracket will be 0. This will be 0. This will be 0. So it means that C2 will be equal to 0. So from here, C2 is equal to 0. Now the second boundary condition is that at X is equal to 12 feet, we have deflection is equal to 0. So you can see over here, X is equal to 12 feet. So we have deflection is equal to 0 because here you can see that this is a roller support. And also the deflection of this beam will be like this. Let me also draw it. It will be act like this. Not like this. It will be, again, let me correct it. This will it will deflect like this. Okay, so put in equation number 2. Put in 2. So we will get this term will be EI into V will be equal to 0 minus 0.25 X will be 12 cube minus 12 minus 6 cube plus 3.75 into 12 minus 12 cube minus 1 over 12 into 12 minus 12 power 4 plus 12 times C1, and C2 is equal to 0. So from here, when you calculate it, this term will be 0, this term will be 0. Only we have 6 cube minus 0.25 into 12 cube plus 12 C1. So C1 will, when you calculate C1, will be equal to 54, and their unit will be gives into feet square. So if you are confused about units, so just forget about it and focus on the remaining problem. Now we are interested to find out maximum deflection in region AB. So we will find this equation of elastic curve. So put C1 and C2 in equation number 2. So what you will get is V is equal to 1 over EI into minus 0.25 x cube minus x minus 6 whole cube plus 3.75 into x minus 12 whole cube plus minus 1 over 12 minus 1 over 12 into x minus 12 power 4 plus C1 is 54, x plus C2 is equal to 0. So this is your equation of elastic curve that is used for deflection. Okay. Now, if you know the value of x, we can see that here the maximum deflection occur that is in region AB. Here this is region AB. But we do not know exactly the location of x where it will be maximum. So we know that the deflection is maximum where the slope of the curve, which is equal to dv over dx is equal to 0. So what we will get the equation of slope from equation number 1. So if you put value of if you put C1 in equation number 1, you will get the dv over dx, and that will be equal to 1 over e into I times minus 0.75 x square minus 3 into x minus 6 whole square plus 11.25 into x minus 12 square minus 1 over 3 into x minus 12 cube plus C1, which is 54. Okay. Now if you put dv over dx will be equal to 0, so you will get the value of x where v will be maximum. So what we will do is that we will put dv over dx is equal to 0 is equal to 1 over e into I into minus 0.75 x square minus 3 into, it will be like x minus 6 square plus this is Macaulay bracket plus 11.25 into x minus 12 square minus 1 over 3 into x minus 12 whole cube plus 54. And you can see that this is the region. So this is 0.6. This is the 6 feet distance. Focus on it. This is 6 feet distance. So this is the x where deflection is maximum. So here you can see that x is greater than 6 and less than 12 is the region where maximum deflection occurs. So I will write region x is greater than 6 feet and less than 12 feet for V max, and dv over dx is equal to 0. So replace x is greater than. So if x is greater than 6, so we will have this value, and if x is greater than 6, for example, and less than 12, so this term will be negative, and anything inside Macaulay bracket that is negative will be considered 0, and this will be also 0. So we will left with 0 is equal to 1 over EI into minus 0.75 x square minus 3 into x minus 6 square plus 0 plus minus 0 plus 54. Okay. So if you multiply EI on both sides, so you will get 0 is equal to minus 0.75 x square, and if you expand it, x minus 3 into x square plus 36 minus 12 into x plus 54. So again you will get, this will be equal to, 0 will be equal to 3.75 x square minus 36x plus 54. So this is your quadratic equation, and you can solve then by using calculator. So if you can see that if you are not aware, so you can just go to this algebra, and here not algebra, you can just go to this is already in this mode. So you can see here, this is the quadratic equation, ax square plus bx plus c. So a is 3.75, b is minus 36, and c is 54. So you have two values, one is 1.86, another is 7.73. So write down this 1.86 and 7.73. So we have x1 will be equal to 1.8, or x is 7.73 feet. Since we are in the region x is greater than 6 feet and less than 7 feet, so x will be this one. So I will write it over here. So V max will occur at x is equal to 7.73 feet. Now we are interested to find out the maximum deflection in region AB. So what we will do is that put x is equal to 7.73 feet in equation number 2, or this in equation of elastic curve. This is the equation of elastic curve. So you will get V max, or you can also say deflection at x is equal to 7.73 is equal to 1 over EI into minus 0.25 into 7.73 cube minus 7.73 minus 6 cube plus 3.75 into 7.73 minus 12 cube minus 1 over 12 into 7.73 minus 12 power 4 plus 54 into 7.73. Okay. So this term is negative, and inside anything inside the Macaulay bracket that is negative will be 0, and this term will be also 0. So after solving this, when you solve this, you will get V max will be equal to 296.77 and divided by EI, and unit will be kips into cubic feet. Now we will copy it and we will move toward next page. Okay, so you have these values. So 296.77 and divided by EE is given as 29 into 10 to the power 3 KSI. So 29 into 10 to the power 3 KSI, and here we have kips into cubic feet multiplied by I. I is 204 inch power 4. 204 inch power 4. Since this is cubic feet, so we'll convert this feet into inch, and 1 feet is equal to 12 inch. So 12 cubic feet, so it will be 12 cube. Now you can see this is kips into feet, and this is KSI. Okay, so when you solve this, you will get maximum deflections comes out to be 0.0867 inch. One more thing is that you have kip above and you have KSI, which is equal to kip per square kilopounds per square inch. So into inch power 4, and we have here inch cube as well because feet is converted into inch cube. So this will be equal to kip into inch power 5 divided by kip into inch 4, which will only left inch. So Vmax is equal to 0.0867 inch, and this is positive, so it means this deflection is upward. Let me show you it as well. So you can see this is positive, so this deflection is upward. And that was all about this problem 12-41. It was a lengthy problem, but I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching.